Hello, y'all, and welcome to lesson 85 of my DP chemistry curriculum. Today we're going over R2.2.9. This is an HL topic. We're going to be talking about rate equations, how they depend on the mechanism of the reaction and can only be determined experimentally. So we're going to deduce the rate equation for a reaction from experimental data. That's what we should be able to do. So with that said, what the heck is a rate equation, or also known as a rate law? So basically, this is a mathematical equation, and it calculates the effect of a change in concentration of reactants on rate. So if it's a fancy way of saying if we change the reactants, so if we change the reactants in equation, how is that going to change the rate? Because one of the things we know from collision theory is that, like, with our rate, it's going to increase with increase in concentration. Because with more concentration, we have more particles moving around, and they're just going to bump into each other more. So an increase in concentration increases the rate. But the increase is not always the same. So it varies from reactant to reactant and from equation to equation. So we have to figure out how to maybe account for those changing situations. Well, if you have some reaction, it could happen in a couple of ways. Maybe your rate doubles as reactant concentration doubles. So that would be like some type of direct relationship. And you might express it as rate is directly proportional to a concentration of some reactant A. So that could be one possibility. Maybe the rate quadruples as concentration of reactant doubles. This could be another possibility. This would be a squared relationship. Like an inverse squared law almost. So rate would be proportional to the concentration of some reactant A squared. And we can kind of see how this is going to go. But what if you have more than one reactant? What if your rate is dependent on multiple reactants? So we have A and B. So maybe our equation A plus B reacts to form AB. And maybe our rate is going to be proportional to A to some power and B to some other power. So this would be a more generic rate equation. This can account for multiple scenarios. So, for example, if concentration of A is directly proportional, then we know that little a is equal to 1, and we end up getting this equation up here. Same thing if B is directly proportional, then we would know that our little b coefficient is equal to 1. if A is squared proportionally to rate, then we know that little a is 2. Same thing for B is squared to rate. Then we know that little b is 2. So that would be taking this one. So if the rate quadruples when our reactant A or B doubles, then we know that smaller coefficient would be 2. One thing that we haven't encountered but can be possible is what if A has no effect on rate? No effect on rate. Well, in that case, A could be 0. Because if A is 0, A to the 0th power is equal to 1, and therefore our equation would just be rate is proportional to 1 times whatever B is to the B. And so we can have no effect, and that would just be a 0 for that exponent. So I'm just going to delete that right there. Same thing with B. If B has no effect, then we know our little b exponent is 0. So we can kind of use this to now determine a rate equation, which is the point of this section. You need to be able to determine a rate equation. So let's go ahead and look at some example. Let's say 2 hydrogen gas plus 2 nitrogen monoxide gas reacts to form 2 water vapor plus nitrogen gas. And in this reaction, we are given that if concentration of H doubles, then rate doubles. We also know that if concentration of NO doubles, we get 4 times the rate. So what is our rate equation? Well, in this case, we know that rate is proportional to the concentration of hydrogen to the first power and the concentration of nitrogen monoxide to the second power, because we have a squared proportionality here, while we have a direct proportionality here, and we would just simplify that to rate is proportional to H squared NO2 squared. Sorry, concentration of H2 times concentration of nitrogen monoxide. Ooh, making a whole bunch of mistakes. Squared. So that is determining the rate equation from given data or given proportionalities. The thing is, when we actually need to find the rate must be determined experimentally. And we have to determine that rate equation experimentally, because the process for which rate expressions are found is through experimental data. That data is taken from initial. So if we remember about our rates, this is taken from initial rate values to determine rate with each reactant concentration. So what the heck does that even mean? Well, basically it means we do a bunch of experiments and we only, for example, in our A plus B becomes AB, we would find the rate of some concentration of A, some concentration of B, then we would double the amount of A and find the rate again. And then we triple the amount of A and find the rate again and see what effect it has. Then we'd go back to our original A and B and now double the concentration of B and find the rate. Triple the concentration of B and find the rate. We don't have to go that far. Usually just doubling it works, but we can now look at some actual data and try and figure out a rate expression. So I'm going to set up an example, pause the video, and we will come right back. All right, so here we go. We have an experiment that had 1, 2, and 3 trials. In the first experiment, we had our initial concentration 0.007 mole per decimeter cubed of A, 0.004 mole per decimeter cubed of B, with our initial rate of 2.25 times 10 to the minus fourth mole decimeter cube inverse second inverse. So moles per decimeter per second. And we noticed between 1 and 2, the only thing we changed in our reactants is we doubled A. When we doubled A, we now look over at our rate. 2.25 to 9.0 is times 4. So we notice here that when this is times 2, this is no change. So we could just say times 1. This becomes times 4. That shows me a squared proportionality. So rate is proportional to A squared. Now, in between trial 2 and 3, this stays the same, times 1, but this is doubled. Our concentration of B is doubled. And here, 9.00 times 10 to the minus fourth to 1.80 times 10 to the minus third is also a double. So this is directly proportional. So we know it's B to the first, but we're not going to write to the first power. So here we go. We have now calculated the rate expression, or sorry, discovered the rate expression through our experimental data. This is it. This whole section culminates to being able to look at some data set and determine the rate expression. That's all you need to do, as well as being able to figure out rate expression through a verbal example as well. If this is something that you can do, then no problem. So I hope this helps and have a great night.